Today's lesson is on the gradients of curves at a point. To give us a historical backdrop to what we're about to learn, let's go back in time to a well-known story about Galileo going to the top of the Leaning Tower of Pisa and dropping two objects of different mass to show that they will strike the ground at the same exact time. By doing this, he's disproving the current, at that time, belief that the speed of an object depended on its mass. And so he disproved this theory by Aristotle, and in its place we have the current idea that the acceleration of objects in free fall come from gravity, the acceleration gravity, which is constant. So it doesn't matter what the mass of the object is, that they should fall at the same speed. And so this opens up a whole new world of questions, and I wonder if any of Aristotle or Galileo's students thought, well, I wonder how fast they were going. You know, if they are constantly accelerating, their velocity is constantly changing, if they're going faster and faster and faster until they hit the ground, how can we find out how fast they were going when they hit the ground? This is the idea of instantaneous velocity, and as it turns out, this mathematically is a very difficult problem to resolve, and we don't really have the tools to do this. And we will try this a little bit later on when we have more tools at our disposal. For right now, we're going to study some problems that I think you will hopefully start seeing the connection between this historical problem and the problem that I posed about the instantaneous velocity when the stones hit the ground with this problem here. But before I go into that, I'm going to give one more real-life example of a gradient of a curve. So if we take the hammer throw, so there's a ball at the end of this chain, and we're spinning it around and around in a circle, the path of the ball follows the circle. But at any given instant, if we were to freeze this motion, what would the direction of the ball be? Well, we would take the tangent to that circle at that point that the ball is at, and if we were to let go of the chain at that moment, the ball would follow the path of the tangent line. And so this is what we're talking about, the gradient of a curve at a point. So let's take a look at a problem that's very theoretical, and eventually as we do these problems we'll be building towards finding a solution for the Leaning Tower of Pisa. But for right now we have this other function, some contrived function here, and what we want to know is, well, what's the gradient of the curve at that point? This would be the same question as if we were to find this point on this curve and we were to find the tangent line through this point, what would the slope of the tangent line be? This is exactly the same question. So we've learned those questions in the previous lesson, and we've learned that we have to find the derivative function. And so here we have the derivative function. All we do now is we just substitute our given value, so the 0.12. As it turns out, the y value is not important to the resolution of this problem. All we need is the x value. Substitute the x value into this function for x. We crank out this number 1, and it turns out the gradient at point P is going to be 1. Okay, let's try another example. There's a slight twist to this. Now they're telling us what the gradient is at point P. They give us the curve. What we need to know is the coordinates of point P. So again, we go straight to the derivative function. We use different notation here. We're using y, and so we use dy dx to find the derivative function. Here it is. We know that this function is equal to 13 at our given point, so we substitute that in. We find out that this point must have an x-coordinate of 2. And so the corresponding y-coordinate will then be, we substitute 2 into the original equation here, and we get 11. So the coordinates of the point that has this gradient must be at 2, 11. A final example, we have this function here, And there are some elements of this function that we don't know. We have a and b. They are constants that are unknown. We have some other given information, namely that the gradient at this point 1, 1 is 5. So our challenge is to find a and b. So again, our first step is to find the derivative function, and we get a formula that looks like this. Now let's take a look at the information that was given to us. We know that at this point we have a gradient of 5. So what we'll do is we'll substitute 1 in for x and 5 in for our derivative value, our gradient. And we can simplify it, and we end up getting a statement like this, which we can't go any further. One equation, two unknowns. What we'll have to do is use some more information at our disposal. We know that this point lies on the curve somewhere. So if we substitute 1, 1 into this curve, so 1 for y and 1 for x, and substitute and simplify, we get this statement as well. So now we have two equations with two unknowns. We can use simultaneous equations to derive that a must be 3 and b must be -2 in order to make all of this true.